In this video, we are going to remind you of a familiar topic encountered in pre-calculus and algebra, the idea of an inverse function. And we're going to begin with a motivating example. I've defined two functions here, or illustrated two functions here, and the question is, can we reverse these functions? So when I say defined or illustrated, for this first example, what I'm thinking is we have a function which sends an input 1 to 3, and an input 2 to 4. So can we somehow define a function that undoes or reverses this? So that would mean I have to start off with the 3 and go to 2, or 1, excuse me, and the 4 and go to 2. And let's maybe just go ahead and call this g. So that works out perfectly fine. G of 3 equals 1, g of 4 equals 2. So in this case, the answer would be yes. I can reverse this first leftmost function. Well, how about for the second function? How we've defined this function is we have f sends 1 to 3 and 2 to 3. And nothing is wrong with that. It's perfectly fine for a function if you have two inputs going to the same output. So that would pass, say, the vertical line test. It's still a function. Now, if we talk about reversing this, we would need to send the 3 to 1 and the 3 to 2. That is, we would need to see g of 3 being 1 and g of 3 being 2. And this is where we run into a problem. I'm going to go ahead and just put a kind of line through this and say this is not a function. So the answer is no, I cannot reverse this, at least in terms of having a function. And it turns out that this idea of reversing a function is really asking, can it have an inverse? And in order for that to happen, what we need is the function to be more like the first example and not like the second example. And the language we have for that is a one-to-one function. A function is one-to-one if it never takes the same value twice. That is, whenever x1 and x2 are different, their associated outputs have to be different. So if you look at our first example, when the inputs are different, 1 is not equal to 2, those associated outputs are different. For the second example, 1 and 2 are different, so 1 is not equal to 2, but their outputs are the same. So the problem with this second example is it is not one-to-one. And from a graphical perspective, it turns out that there's a really nice way to see if a function is one-to-one. It's one-to-one if and only if it passes a horizontal line test. No horizontal line intersects the graph more than once. So y equals x to the left here, draw your favorite horizontal line, does not matter which one. It's always going to intersect in exactly one spot, but no more than one. So y equals x is 1-to-1. Now y equals x squared is a bit different. If you draw a horizontal line which corresponds to a negative y value, it does not intersect the curve at all. That's perfectly fine. But with a positive y value, it intersects the curve in exactly 2 spots. So y equals x squared is not 1-to-1. So what does this idea have to do with an inverse function? And we have the following definition / property here. If f is a one-to-one function, then it's going to have an inverse. The inverse function we denote by f raised to the -1 power. If f has domain A and range B, then for the inverse function we flip those around. The domain becomes B and the range becomes A, and the reason is because of how we define it. The inverse undoes the function. So if f inverse of y is equal to x, that must mean that y is the thing that comes from plugging x into the function. You're undoing that relationship. Now let's just think about this for a moment in this graphical perspective. So I've drawn the sketch of a function y equals f of x, and it has a point on it x comma y. What that is telling us is that when we plug in x, we get back y. So in terms of our above definition, this means that when we plug y into the inverse, we must get out x. So a point we know that would be on the graph of y equals f inverse would be y comma x. And from a graphical perspective, if you compare the point x comma y and y comma x, what happens is that should be a reflection about the line y equals x. And in fact, if you have the graph of a function, its inverse is going to be the reflection of that graph over the line y equals x. So in this case, if we were to complete the graph, y equals f inverse would look something like this. So in blue would be y equals f inverse of x. So just a nice graphical perspective to keep in mind. The relationship between the graphs of a function and its inverse is that they are reflections about the line y equals x. Another nice property is that we can use calculus to determine in certain scenarios when a function has an inverse. And the property is as follows. If f is a strictly monotonic function on its domain, then it has an inverse. Now, what do we mean by strictly monotonic? What that means is that the function f is either increasing or decreasing. So it's doing either entirely one or the other. Now, from a calculus perspective, remember what increasing would mean is that when you take the derivative of the function, it's always positive. What decreasing means is if you take the derivative of the function, it is always negative. So from a calculus perspective, if the derivative is always positive on the function's domain, then it has an inverse. If the derivative is always negative on the domain, then the function also has an inverse. And let's put this to work for us. Let's show that the given function has an inverse, and then go ahead and find a formula for that inverse. So our function is the line 5 minus 4x. So f prime of x in this case is minus 4. And regardless of the input, our domain is all real numbers. This is less than 0. So our conclusion is that since f is monotone, and in this case that monotone is really a decreasing function, what we know is that f has an inverse. And since we know that f has an inverse, we technically should be able to find it. And this is really kind of an old idea from pre-calculus, but let me remind you how this works. We write down y equals our function, and what an inverse is doing is really kind of, an inverse is undoing the function. So undoing the function, I want to go from y equals a function of x to instead x equals a function of y. So what I'm going to do is isolate x. So we have y minus 5 equals minus 4x. And if we divide by minus 4, we have that x is equal to 5/4 minus 1/4 y. And once we have solved for x in terms of y, what we do is we interchange those variables. That is, I now write it as y equals 5/4 minus 1/4 x. And when we do so, this function that we have for y is really f inverse. That is to say, in this case, f inverse of x is equal to 5/4 minus 1/4 x. Now, we can check this, so to speak. So kind of an additional observation is that if you have f and f inverse, those functions should undo each other. So if you calculate out f of f inverse of x, what you should get back is x. And similarly, f inverse of f of x should also give you back x. So if I want to calculate f of f inverse, I need to go up to my function f, and wherever there is an x, I need to replace it with f inverse. So that would be 5 minus 4 times f inverse. 5/4 minus 1/4 x, because our f inverse is getting plugged in. So the 4 distributes through and cancels. What we are left with is 5 minus 5 plus x, which equals x. So f of f inverse should equal to x, and I'll leave it to you to check. F inverse of f of x should also be equal to x. So to summarize, just from a more procedural perspective, if you would like to find the inverse of a one-to-one function, so the one-to-one is important here. You should know that the function has an inverse before you start trying to find it. You write y equals a function, and just like we did previously, you solve for x in terms of y, interchange the x and the y, and once you've interchanged the x and the y, the resulting equation is f inverse. So let's practice with one more example. So we're going to consider the function f of x equals x over 1 minus x. So let's first think about why it has an inverse, and of course we're going to think from this calculus perspective. So f prime x, if it's either entirely positive or entirely negative, we would know it's monotone and would have an inverse. So let's differentiate with the quotient rule. The quotient rule tells us low d high minus high d low, all divided by the bottom squared. So in the top, if you think about distributing through, you have 1 minus x, then you have minus a minus, so plus x. So 1 minus x plus x is just 1, and this is all divided by 1 minus x quantity squared. And if we have 1 over 1 minus x squared, that's going to be positive, on its domain. And note, what is the domain of this original function? X cannot be 1. X cannot be 1. So f prime is positive, which means that f is monotone, and hence has an inverse. So f is monotone and must have an inverse. And since it has an inverse, we're going to go ahead and find it. And we're going to follow our procedure from the previous slide. The first thing we do is we write down y equals f of x. And then what we do is we think about undoing this. I want to write it as x equals a function of y. So let's just kind of algebraically solve for x. So multiply both sides by 1 minus x. And then group together all of the x's on one side. So on the left, we can think of this as being y minus xy equals x. Y equals x plus xy. So y equals x times the quantity 1 plus y. And lastly, divide both sides by 1 plus y, and we have x equals y over 1 plus y. So once we've solved for x as a function of y, we interchange our variables. So y equals x over 1 plus x, and what remains is f inverse. So in summary, if a function is monotone, that would mean that, say here in this case, its derivative is always positive, so increasing, or its derivative, as in the first example, is always negative, which means decreasing, it will have an inverse. And since it has an inverse, we should be able to algebraically
solve for.